Okay, chapter 11. So, chapter 11 is about heat exchangers. Now, what are heat exchangers and why are they important? So, heat exchangers are devices that allow heat exchange between two fluids at different temperature that are separated by a solid wall. So, a simple example of a heat exchanger is the radiators that are located in front of your cars, which help in cooling the engine. So the radiators, there's a coolant that runs inside the radiators, and air flows across the tubes of the radiators, thereby exchanging heat. So that's one simplest practical example of heat exchangers that we see on day-to-day basis. Now, there are different types of heat exchangers, and based on applications and based on what type of cooling is favorable, we select what type of heat exchanger we need. So, the two types of heat exchangers are concentric tube heat exchangers. So, this figure here shows, and they are of two types, so parallel flow and counter flow. Now, what does concentric tube mean? That means that the inner tube is running inside a larger tube, and the flow in both these tubes are moving in the same direction. So if you see, the flow in the tube in the smaller tube or the inner tube is flowing from left to right, and the flow in the outer tube, which is surrounding the inner tube, is also flowing from left to right. So that's why it's a parallel flow. Whereas in figure B, the flow is in opposite direction. So the flow in the inner tube is going from left to right, but the flow in the outer tube is going from right to left. So that's why the flow are in opposite direction, and hence it's known as a counterflow heat exchanger. Now, you may have some complex heat exchangers. So, so these are of two types. So you can either have fins to these heat exchangers. So if you don't have fins, you'll just have multiple tubes uh, which will be flowing some fluid, which is either hot or cold, and there might be air that's flowing across it. So in figure 11.1, we had a flow either in parallel or counter flow, but it was in the same direction, in the same plane. But here you have cross flow, so the cylinders are or the tubes are running in a different plane and the flow is in a different plane. So you can assume that this is your radiator which is running the coolant inside it, and just to enhance the heat exchanger, we have added fins to these tubes so that the fins can enhance the rate of heat transfer and be more efficient. There's another type of heat exchanger which is called as the shell and tube heat exchanger. So this is a combination of both. So what happens here is that you have a tube which is inside a shell, which looks like this, and you create a counterflow. So you add baffles to this shell so that your flow will, so there's some coolant or refrigerant which is flowing inside the tube like this, and there is some let's take this color, and there's flow in this shell which will move in this direction. So it will be a cross flow, and then it will exit the shell. So uh, we do this to maximize the contact area between the tube and the air flowing. So this makes the system more efficient. So we have seen this equation before. It's the equation of the overall heat transfer coefficient, and the overall heat transfer coefficient is usually combined with the area. So if you are taking the overall heat transfer coefficient with respect to the cold fluid, you'll have to multiply by you will have to use the area of the cold fluid or the hot fluid, and it will be the combination of all the resistances. So in this case, you have a cold fluid, you have a hot fluid. This is the heat transfer coefficient of the cold fluid times the area, uh, contact area of the cold fluid, plus Rw here is the contact resistance. Because these two fluids are separated by a solid wall, there might be some contact resistance and heat resisted due to that. So we consider that as well. And if we add fins to this, our equation changes. We get an efficiency term here, and we also see another term which is this R double prime FC, and that R double prime FC is the fouling factor. Now what happens is that when you have continuous flow flowing through these pipes or through these tubes, you may have some fouling due to fluid impurities. So let's say you have some oil flowing. That oil, there might be some impurities from those oils that might be deposited on the surface of the tube, or your tube might rust if there's steam flowing through it, or if you have hard water and you are maybe cooling or heating that water, there might be calcium deposits or there might be scaling, which again opposes the transfer of heat or acts as an additional resistance. And that's why we include that resistance while calculating our overall heat transfer coefficient as well. So you need to make sure that whenever you solve a problem, uh, if you have fouling or contract resistance mentioned, you have to consider that. Else you have to state it in your assumptions that you are ignoring the effects of fouling or contact resistance. Now moving on, in table 11.1, your textbook states the fouling factor for different scenarios. So if you have seawater and treated, so if you have seawater, your fouling factor is 0.0001 meter square Kelvin per watt. And if you have fuel or refrigerant liquids, these values will differ accordingly. So if you get any problem which has fouling factor, refer to table 11.1 and choose the appropriate value of the R double prime F and then solve the problem. Now the eta 0 that you see here is the overall surface efficiency or the temperature efficiency, and we'll see what that is. So as we know that there is some loss of heat, or the heat transfer between the surfaces is not always 100%. So we can say that the heat transfer rate Q is equal to that efficiency times HA times TB minus T infinity, where the eta 0 is represented as 1 minus AF, that's the area of the fin, divided by the total area into 1 minus efficiency of the fin, where eta F is the efficiency of the fin, and which we've already seen in our previous chapters, that let how to calculate this efficiency of the fin. So for example, if we have an adiabatic tip and a cylindrical fin, our eta f or the fin efficiency will be hyperbolic tan of ml divided by ml. Okay, so moving forward to heat exchangers and calculating the heat transfer in heat exchangers. So let's say we have a heat exchanger, or we have two fluids flowing parallelly to each other. A hot fluid flows in the upper half of this shell or a tube, and a cold fluid flows in the lower half. The mass flow rates and the temperatures at inlet and outlet are given. And obviously, because of the temperature difference, there will be heat flowing from the hot fluid to the cold fluid. Now the heat being transferred in the hot fluid will be m dot Cp of the hot fluid times the temperature difference of the hot fluid. So as the fluid moves from inlet to the outlet, it will it will lose Q amount of heat, and as the cold fluid moves from the inlet to the outlet, it will gain Qc amount of heat, which will be m dot C into the specific heat capacity of that cold fluid times the temperature of that cold fluid at inlet minus temperature of that cold fluid at the outlet. Now the Q here is the heat exchanged between the hot fluid and the cold fluid, which I have represented as QHC, and that is represented by the overall heat transfer coefficient times the area, which will be this area here, times the delta Tm, where delta Tm is the mean temperature difference. Now let's look at each type of heat exchanger, and let's try to find out what will be the heat transfer rate in each case. So our first type of heat exchanger is the parallel flow heat exchanger. So let's say this is our parallel flow heat exchanger. Again, we have hot fluid moving in the upper half, cold fluid moving in the lower half, and we take a small control volume of thickness Tx. So the heat entering into this or the temperature of the fluid entering into this control volume is Th, temperature leaving is Th plus dTh. Similarly for the cold fluids, and heat is being exchanged between the hot fluid and the cold fluid. And these tubes or this heat exchanger is insulated on both sides. So the heat exchange is only between these two fluids, and there is no heat loss to the surrounding. So what happens is that at the inlet there's a temperature difference between the hot fluid and the cold fluid. So the hot fluid is extremely hot and the temperature is Thi, and the cold fluid is extremely cold and the temperature is Tci, and the temperature difference between them is denoted by delta T1. Similarly, at the outlet, the hot fluid has lost some heat and the temperature has lowered, so it's at temperature THO. O stands for outlet, and the cold fluid has gained some heat and is at a temperature of TCO, and the temperature difference at the outlet is now delta T2, which is THO minus TCO. So let's say that the temperature difference at that particular element is at that particular x where we've taken the control volume is delta T, and we can write the dq, that is the exchange of heat between these two fluids, as minus m dot h Cp into dt, and minus sign because it's losing heat, and I can write the m dot into Cp as a uppercase Ch, which is the heat capacity rate for the cold fluid and the hot fluid. So for the cold fluid, I'll write it as heat capacity, that's the uppercase C H into dTh, and for the cold fluid it will be a positive sign because it's gaining heat, and, and it will be C times dt of the cold fluid. So we know that our heat exchanged is the overall heat transfer coefficient times the area. Area in this case is that area dA times the temperature difference delta T. That's the temperature difference between the hot and the cold fluid. So delta T is Th minus Tc. And if I differentiate this equation here, if I differentiate delta T, I get dTh minus dTc. Now we've already calculated dTh and dTc here, so I'll replace these values in these equations, and I will get d of delta T as minus dq by CH, and this minus sign comes from here. And for the cold fluid, because we have a positive sign, it will be dq by cc. Now on integrating this and substituting it in this equation, we get our q as ua times delta T2 minus delta T1 divided by the natural log of delta T2 by delta T1. And we have seen this expression before. It's nothing but the log mean temperature difference. So I can write the Q, that's the heat exchanged between the two fluids, as the overall heat transfer coefficient times area times the delta times the log mean temperature difference. So this is how you calculate the heat transfer rate between the two fluids of a heat exchanger. And our delta T1 here is Thi minus Tci. So delta T1 is Thi minus Tci, and delta T2 is Th2 minus Tc2, and this is for a parallel flow exchanger. Now what if we have a counterflow heat exchanger? For a counterflow heat exchanger, our one fluid will be going from left to right. So let's say the hot fluid is moving from left to right and the cold fluid is moving from right to left. And let's take the same element. Now the now let's look at the inlet. So at the inlet, or let's say this is location 1. Let's say at location 1, our hot fluid is at temperature Thi because it's entering at this location, and because our cold fluid is leaving, it has already exchanged or gained heat by heat exchanger by exchanging heat, and it is at a higher temperature, so it's at a temperature of TCO, which is higher than its initial temperature. Similarly, at location 2, the hot fluid has already lost some heat, so it's at a lower temperature than inlet, and the cold fluid is entering, that's why it's at a lower temperature. So this is delta T1 and delta T2. So the only difference between the counterflow heat exchanger and the parallel flow heat exchanger are delta T1s and delta T2. So for a counterflow exchanger, our delta T1 will be Thi minus Tco, whereas for the parallel flow heat exchanger, our delta T1 was Thi minus Tci. And similarly at location 2 for counterflow, it is Tho minus Tci, but for parallel flow it was Tho minus Tco. So that's the major difference between the uh, parallel flow and the counterflow heat exchanger. Otherwise the formula will still be the same. Our delta T Lm, that's the log mean temperature difference, will still have the same formula. Now the only difference here is that because your delta T1 is smaller in this case, your delta T Lm for a counter flow is larger than delta T Lm for a parallel flow, and that is because of this temperature difference here. So if we see delta T2 minus delta T1 is a small value for our counterflow heat exchanger, and that's why we have this condition right here. Okay, so moving on to effectiveness of heat exchangers. Now the most effective heat exchanger is the counterflow heat exchanger, and the maximum effectiveness can be achieved if we use an infinitely long counterflow heat exchanger, or if one of the fluid, and if we have uh, an effective heat exchanger, one of the fluid will experience a maximum temperature difference, and that will be Thi minus Tci. So what this means is that if you have a hot fluid that's entering in a counterflow heat exchanger, by the time it exits the heat exchanger, its temperature will be Tci. So for hot fluid, we have Thi minus Tho as the temperature difference, right? But because the heat exchanger is so effective, our Tho will be equal to Tci, and that's the maximum temperature drop that can be achieved in any heat exchanger. So now let's consider our heat capacity rate for our hot fluid is larger than the heat capacity rate of our cold fluid. Now we've seen that the relation between C and dt was inverse. So this will mean that dt for C, the absolute temperature difference for the cold fluid will be larger than the absolute temperature difference of the hot fluid. Now what this means that the cold fluid would experience a large temperature change, and since the length, we have an infinitely long heat exchanger, our TCO will be equal to Thi, and that's what I said here. So that means that your maximum heat transfer rate will be your heat capacity Cc times Thi minus Tci. And if the maximum temperature change is for the cold fluid, for the hot fluid, that means if your C is larger than Ch, that means that your C max will be Ch times Thi minus Tci. So if we generalize this, we can say that our maximum heat transfer rate is equal to C min times Thi minus Tci. So Thi minus Tci is the maximum temperature difference that can be achieved by any fluid in the heat exchanger. So your hot fluid cannot be colder than the cold fluid flowing, or your cold fluid cannot be hotter than the hot fluid. So that's the maximum temperature difference that can be achieved for any of the fluids that's flowing, and it will be achieved for the fluid which has a smaller heat capacity rate. So C min here is the heat capacity rate, and minimum stands for whichever of the two fluids has the smaller value. So if Ch is smaller than Cc, we will substitute Ch here, or if Cc is smaller than Ch, we'll substitute Cc in this equation right here. So this is a very important equation that you must know. For a counterflow heat exchanger, the maximum effectiveness is achieved if the heat exchanger is infinitely long, and what will happen is that we will have a maximum temperature difference, and that will be achieved for whichever fluid has a smaller heat heat capacity rate. Now we haven't defined the effectiveness yet. So the effectiveness is defined as Q divided by Q max, which is the actual heat transfer rate divided by the maximum heat transfer rate. So the maximum heat transfer rate is what we've calculated here, and the actual heat transfer rate is whatever temperature differences and heat capacity rates are there. So if we are looking at the effectiveness with respect to the hot fluid, our actual heat transfer rate would be the heat capacity rate of the hot fluid times the temperature difference of the hot fluid, which is Thi minus Tho. So temperature at inlet minus temperature at outlet, divided by the maximum, which is Qmax. Or if we are looking at it with respect to the cold fluid, it will be Cc, that's the heat capacity rate of the cold fluid, times the temperature difference of that cold fluid, which is temperature at outlet minus temperature at inlet, because outlet will be at a higher temperature, divided by Q max, which is this value right here. So this is how you calculate the effectiveness of a heat exchanger. You calculate the Q max, and then you divide the actual heat transfer rate by the maximum heat transfer rate. Now, obviously, the effectiveness of any heat exchanger will lie between 0 and 1. And if you know the effectiveness of a heat exchanger, you can calculate the actual heat transfer rate by multiplying the effectiveness by the maximum heat transfer rate. So in this case, you will just need to know what is the heat transfer, what is the specific heat capacity rate of the fluid, or one of the fluids which has, and choose the heat capacity rate of the which is lower, and you will just need to know the conditions at the inlet of the hot fluid and the inlet of the cold fluid. So if you know the conditions at the inlet of the hot fluid and the inlet of the cold fluid, you can and the effectiveness, you can calculate the actual heat transfer rate of that heat exchanger. Now this heat exchange, the effectiveness eta is a function of NTU and uh, the ratio between the minimum and the maximum heat capacity rates. Now, but what is the NTU here? So the NTU is something called as the number of transferred units. So it's a different way of looking at how much heat has been transferred. So instead of quantifying heat transferred in terms of watts, we quantify it for heat exchangers. We quantify the heat transfer, or as number of transfer units. So how many units of heat was exchanged or was transferred between the two fluids. And the formula for NTU is the overall heat transfer coefficient times the area divided by the minimum heat capacity rate. And the relation between NTU and effectiveness varies for different geometries and different types of heat transfer uh, different types of heat exchangers. So you'll have a different relation if it's a concentric tube and parallel flow, or a counter flow. If you have a cross flow heat exchanger, and if you have baffles, or if you have fins, you will have a different relation, and the relations are given in table 11.4. So this table looks something like that. So for a parallel flow heat exchanger, if you know the ratio between your Cmin and Cmax, so let's say if your cold fluid is has a smaller value than your hot fluid, you'll divide the heat capacity rate of the cold fluid by the hot fluid, you'll get Cr, and that's the only thing you will need to find the effectiveness of that heat transfer heat exchanger. So you see that it has a bunch of different relations, uh, and for different types of heat exchangers. So you need to identify what the problem states and what type of heat exchanger is given in the problem. Then identify which of the two fluids has the smaller heat capacity rates, and then calculate the effectiveness through these relations right here. Okay, so this is how you approach or solve heat exchanger uh, problems related to heat exchangers. The things you may be asked are, what is the number of transferred units? What is the effectiveness of the heat exchanger? What is the maximum heat that can be exchanged between the two fluids? And you can be asked these for different types of heat exchangers.